Patrick tries to kick a rugby ball over a crossbar of a goal. The feet of the goalposts are 13 meters away from the point where he kicks the ball. The vertical height of the ball in meters is approximately modeled by that function, where x is the horizontal distance from where it was kicked. So we've got a quadratic equation. First things first, graph it. We need to make sure that we fit it. I first start by doing a standard zoom, and then I try and fit. Again, not super helpful. Instead of zooming out though, because I can definitely see that curve, I'm going to click and hold in the white space so I can bring it over, because I think I'll just be able to see it like this. Perfect. All right. We have this graph right here. We've just graphed it onto our calculator. Try and envision, again, take a moment, put it in the context, think about it real world. What is happening here? What are we talking about? Well, we're talking about somebody standing here and kicking a ball and 13 meters away. So 1, 2, 3, 4, 5, 6. 13 meters away is where the goalpost is. And realize that that's not where the ball stops, right? 13 meters is a little bit towards the end. So if we wanted to envision this, Patrick, goalposts, and then he kicked a ball, and at some point it went in or something, right? But we haven't fit a full parabola before it hits the goalpost, hopefully, potentially. So taking a second, making sense of it. You can draw a quick little sketch, say, hey, that's 13 meters. Cool. Draw it on your calculator. Plot it on your calculator. All of those are good things to do when you start a problem. Find the maximum height of the rugby ball. Okay, well, your maximum is going to be in here, and you can just use your calculator in order to find that. Go ahead and answer for the maximum height. So, number one mistake a lot of students make is that you find the maximum, which has the coordinates of 7.5, 5.63, and you give me the coordinate of the maximum, but that's not what the problem is asking. The problem is asking, what is the maximum height? Which variable represents height? Well, x represents horizontal distance, and y represents height. So it's only looking for the y value here. So your maximum height is 5.63 meters. Find the coordinates of the y-intercept and explain what this tells you about the height from which Patrick holds the ball. It looks like that it goes through 0, 0. You can always do a quick trace to double check. Your y-intercept happens when x equals 0. So if you're tracing and you just do 0, enter, it shows you what that coordinate is, 0, 0. The y-intercept is 0, 0. And what does that mean about the height in which Patrick kicks the ball? Well, at horizontal distance 0, where we start, the initial height, remember that your y-intercept is always talking about initial things. Your initial height is, well, the initial height is 0. Which does mean something in the context of a sport, right? In a sport, you can pick up the ball and kick it, punt it, right, when you're holding it up. But sometimes it's also on the ground and you kick it from the ground. So it does mean something different, and it does tell us something helpful. Okay. Given that the crossbar is 2.5 meters above the ground, determine whether the ball passes over the bar. Going back to your picture, which is why it's important to have a picture. Remember that 13 meters happens before it hits the ground. And our question is that as it gets to 13 meters, where the goalpost is, the crossbar is, did it go under, did it go over, or did it hit exactly the height of the crossbar? Well, the height of the crossbar is 2.5. So we want to know is at this point, right here, 13 meters away, is it 2.5? Is it above 2.5 or is it below 2.5? Did it get in the net? Did it do great at the crossbar challenge, or did it totally whiff and go somewhere else? Okay. So given that the crossbar is 2.5, determine whether the ball passes over the crossbar. There's a couple ways that you can do this. You can try and figure out at what x value at what horizontal distance would your height be at 2.5? Or you can say at 13, where the crossbar is, are we at 2.5? So that's what I'm going to do. I'm already tracing, right? The little x there is showing me that I'm in trace function. So I want to know what is my y value when x equals 13. So I can literally just type in 13, and here it says x equals 13. I press enter, and it tells me what the y value is at 13. So I can say f of 13, or in other words, when x equals 13, 13 meters away from where I kicked the ball, or Patrick kicked the ball, y, or the height of the ball, is 2.6. Okay, so when we kicked the ball, it gets to the goalpost, to this crossbar over here, and instead of being at 2.5 where the crossbar is, it's now 2.6. It's slightly above the crossbar. So that's the answer there. The ball crosses over, crosses the crossbar. Since at 13 meters away, because we need to justify, we need to say this is why. The ball is 2.6 meters high. Okay. Example 3, our last example. At a school sports day, Petra has to throw a shot put. The path of the shot put follows a parabolic curve given by the equation where t is time. Okay, interesting. We haven't talked about t as time or as your input as time. We've done a lot of horizontal versus vertical, right? So now instead of it being the actual visual path of the ball, right? This is what the ball would look like across by your eyes. When we have x, your input, or t in this case, your input being time, you're now looking at just a relationship between time and the height. F of t is the height in meters above the ground, right? So it could go up, 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 and come down, 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 down. But it could go just like straight up and down, or it could go like really far and then down. But your graph is going to look the same if it takes the same amount of time. So it's not an actual visual representation of what it looks like as it travels when t is a function of, when f is a function of time. We'll talk more about that if that didn't make sense. Here we've got our equation. First things first, if you're given an equation, the first thing you should do is graph it. So hopefully you've already, while I was rambling, started to graph it. And yes, it says t, but we do x instead. And there we go. This is already scaled perfectly, so we don't need to do anything. And we've got this path going on right here. Initial height, right? So it starts at what looks to be 2 meters, starts at 2 meters. That's about the height of somebody, right? So if they're doing a shot put, it being released up 2 meters up the ground, from above the ground, that makes sense. And then we have this path, but remember that this is not a visual representation of the path. It didn't go like that. This is just saying this many seconds in, this is how tall it was. But it could have been very short or it could have been very long, and that doesn't make a difference in this graph. However, we do want to find the height of the shot put after 5 seconds. So I think you can go ahead and do that on your own. 5 seconds. Time is 5. Okay, so I'm plugging in 5 for t. In other words, I'm plugging it into my input. You can use your graph and trace and hit 5, enter, and it tells you what it is to 3 significant figures always. So that's pretty sweet. 3.94. Whoops. F of 5 equals 3.94 meters. So at 5 seconds, it's 3.94 meters in the air. Find the time, when the height of the shot is 3. So height is f of t equals 3. Okay, so then t equals what? This moment of extrapolating pertinent information is a very important part of preparing for a problem. So labeling it out is going to help you figure out, where does this number go? Well, it doesn't go in for t because we're saying this whole equation is going to be equal to f of t. So instead of f of t, I replace it with 3. So I could say 3 equals Now, there is no nice way to do that on the calculator. There just isn't. Not like we were able to do for part A. So what we do instead is we can graph a second equation in which y equals 3. F of 2 or f2 of x equals 3, and I graph it. And we see here now, this is where all x values will provide us with a y value of 3. Everywhere along this line has a y value of 3. So where it intersects our graph will guarantee that that's where our graph has a y value of 3. So that will have a y value of 3, and that will have a y value of 3. We just need to know the x value that gives it to us, which means we need to find where they intersect, which we talked about how to do in previous units. A great place to start always is your analyze graph. Go ahead and tell me the 2 different places where it gives us a y value of 3. It tells us at 2 and 10. So t equals 2 seconds and t equals 10 seconds. So 2 seconds in, it has a height of 3 meters. And then once it starts coming down, 8 seconds after 2 seconds, so a total of 10 seconds after the throw, but 8 seconds later, it also has a height of 3 meters. And there you go. You could use numerical solve to solve for this. I wonder if some of you went to go do numerical solve. Numerical solve will only give you, actually, I'm not sure. Let's go look. I was just about to say that numerical solve will only give you one answer, but let's see what happens. 3 equals. Remember to do comma and the variable you're trying to solve for. And all it tells us is 2. So numerical solve would only give you one answer. And if it's squared, it's possible it would give you 2 answers. If it was cubed, it's possible it would give you 3 answers. So in order to find all of the solutions, using your graph instead is the best way to handle those problems. So just be aware of that. All right, that's it for today. Good job.